Hi Janice, hi Jayanta. Nice seeing you connected.
Nice to see you too.
Oh, hi Kristen. Nice seeing you connected. Microphone is not working. My microphone is not working or your microphone is not working. Oh, okay. Um, so I was sending a request for assigning the room QBB 132 for this class. I'm just a little lazy to go there myself, but it should be activated and open right now. So maybe there is a microphone and camera and computers there. So as a backup, we may try to go. Whoever needs may try to go there at the time. Oh, okay. But I'm reading the comments, so do not worry if microphone is not working. Okay. So maybe a couple of minutes more. Okay, I believe I will better start, and whoever um, will be missing our meeting can read it can watch it from the recordings. I believe the recording is going on. So this is summer version of the computational chemistry course. The goal of the course is to overview some background theories and concepts, and then run correct software on correct hardware to characterize molecules and materials and compare them with experiment as a complement to primary research activities. So here is the sign up list. So I think it is a very good settings, and there was a suggestion to um, migrate the presentation day to another date. So we can discuss it on coming Wednesday. And I have forgotten, I want to share the examples, templates of the presentations. But even if we are presenting not on the lucky day of 13, please consider to complete your slides and send them to me by Sunday midnight, so I can glance over and generate suggestions or use them for presentations in the same style as we did before. So the let me select highlighter. Yes. So today we will cover last 3 lines, and I do not know who will be presenting density density of states. So this is primary, maybe one of the main observables in the course, and I will check if Mahima will be interested and available, but we will discuss how to have these subjects covered. So here is the list of chapters and subjects. So the plan is to, well, I do have slides for about 4 chapters and 30 meetings. And since summer semester is shorter than fall and spring, we may sacrifice some meetings from the end, but I will try to squeeze rather than sacrifice. The lab today, let me go over the lab and briefly cover what will be today after brief overview of theoretical parts. And what we are going to oh yeah, Joanta, thank you for supporting this idea. Yes, I please send me a reminder by email, maybe in the middle of the night today, like few hours after our meeting is done. So I will before we go to theory, I want to give a heads up about the practical part of the lab, and a very brief overview. What is the goal? You already know how to plot density of states, and you do know the definition of density of states. So it is something that can characterize any material, any molecule, independent of number of atoms. And there are electrochemistry and scanning tunneling microscopy experiments that help to directly measure density of states. Orbitals. Oh, hi Lishu, nice seeing you. Lishu, do you have the link to the presentations sign up? I can oh, okay, yeah, it's good if she thank you, Joanta, but I want to match the schedule. Some of us are not ready to stay past 7, and I better squeeze material before the end of the class. So, Lishu, do you see the link in the email? So let me bring it up. So there is a link. Please select what you would you like to present in a week from now. So we need to get a quick refresher of lab materials, and right now we need someone for density of states per scripts that we were doing last Wednesday, and for mimic and charge analysis and OpenShell. So the link is available for editing, so you can just type in your name near the subject that you are interested to present. And I will go forward with materials, but I will check later what is your choice. So what are we going to do? Oh, hi, Mahima. I am very happy to see you connected.
Yeah, hi.
Okay. So we do have at least two, maybe more researchers who. And by the way, if you're not speaking, it's better to turn off the microphones. But as soon as you speak, turn them, unmute them back. So, thank you. Mahima and Gianta are experienced in wet synthetic chemistry and aware of metal-organic complex and catalysts. And I think all of us are acquainted with this concept. So when we do have a transition metal ion surrounded by organic ligands, it is very often that this system has odd number of electrons. Not 10, not 12, not 100, not 102, but odd number, like 101, 203. So odd number of electrons with unpaired electrons. And we do need some basic skills how to treat molecules and materials with odd number of electrons. This is especially important for metal-organic catalysts, like nickel catalyst in Mahima research, and I think there could be some indium catalysts in Gianta research, and all of us run into those often. So one can modify number of electrons for our model from previous example, but this model with titanium hydroxide is typically has even number of electrons, so it's not a good example. But if we take the more realistic hexa-aqua complex of the titanium 3, then it comes to most stable configuration in when the titanium ion has 3+, and in order to stabilize it, it has octahedral coordination to 6 water molecules. So we will be doing a couple of examples related to this complex, and most interesting, most important part that so before we used to have this charge and multiplicity 0 and 1, and here in this example that we will cover today, so titanium 3+ is coordinated with 6 waters. So since the overall model is 3+, we will put charge 3 in here. And then in our previous model, titanium was 4+, so the number of electrons was even. But now we have odd number of electrons. It automatically require multiplicity different from 1. So specifically here, it will be 2. And the plan and goal is to plot density of states which will be separate for electrons up and for electrons down. And as you see here, they often do not coincide. So there are peaks specific for up and down, specific for alpha and beta electrons. Then, if we have separate energies, different energies for alpha and beta electrons, their orbitals are will also look differently. So we will use these keywords AMO and BMO to generate orbitals and plot them and compare if they look similar or different. And there is a way to generate few more things out of form check. So density, spin, and electrostatic potential, ESP potential. And in Gauss view, one can watch relative charge on each ion. So green and positive number means it is plus. Red and negative number, it means like oxygens here are minus. So if hi you, I see you connected. Welcome to this meeting and hello. So what we will be doing after a brief summary of lecture, the different charge and multiplicity could be important for your research as well if the models are coming into doublet or triple configurations like defect nanotubes. So one needs this skill for multiplicity different from singlet. Okay, so I'm going to briefly, I will try to briefly review what we were doing in the last 4 lectures and then do one more on Hartree-Fock theory. So one of the fundamental concepts for multi-electron wave function. So we give up modification of nuclear positions and focus on the electrons. And there are many electrons, and one needs the concept of Slater determinant, which is like for 2 electrons and 2 wave functions, it is diagonal product minus off-diagonal product. If it is bigger number, it is same as in linear algebra. Here is a brief sketch of the plan how we go through this chapter of Hartree-Fock. So we start from Slater determinant, then we briefly looked on spin concepts to justify shape of Slater determinant. Then we jumped on a new disconnected on the concept of so-called mean field, how the rest of electrons affect the last electron through Coulombic attraction. And then last time we considered variational theorem. So we are going to, last time we did start, and today we will continue the Coulomb and exchange types of electron-electron interaction, and I will try to introduce concept of one electron Fock operator, and then next meeting we will combine all these concepts into the flow chart for the Hartree-Fock theory that is being executed when we run Gaussian. So repeating this little recital once again. So we are solving an electronic problem for the wave function, and the Hamiltonian includes kinetic energy of electrons, potential attraction between electrons and nuclei, and repulsion from electron to electron. Wave function is searched in the shape of Slater determinant. Since electrons are repelling from each other, if we ionize the molecule and then return electrons back, if you throw them back, then each next electron has less chances to be attracted to nuclei because previous electrons already take their spots in space and repel next electron. Therefore, all orbitals have different shape. We also were playing to a wheel of fortune for expectation value principle, and through this expectation by practicing partial expectation value in respect to not all electronic degrees of freedom, but all but one, we can replace multi-electron Hamiltonian into single electron Hamiltonian. So whatever we have in a bracket does act on the electron number 1 as operator, but does not depend on position of second, like does not affect second electron, even if you would have it. And the same thing can be done for the second electron. So by doing this partial convolution of the Hamiltonian, we are getting pseudo Hamiltonian that acts not on all electrons, but only on one electron. Another concept is variational theorem. Suppose that we know the wave function for sure, absolutely correct wave function, many electron wave function of all electrons for the molecule. And then we try to slightly modify it by bringing a little addition to wave function. And it doesn't necessarily need to be positive, it can be negative. But the variational theorem tells that the energy of the psi naught will be always smaller than energy of psi naught plus delta psi. So no matter how we change ideal and correct wave function, any changes to wave function will increase the energy. And when we were meeting last time, we did set up a hierarchy of objects. So atomic orbitals are used to compose molecular orbitals. So by superimposing several atomic orbitals on different atoms, one is getting molecular orbitals. It is what we are drawing during our lab part. And when we are setting up a line of all objects, so we start from positions of ions when we do calculations, and we end with total energy. And in between, we are going through hierarchy from atomic orbitals to expansion coefficients to molecular orbitals to wave function. And the only thing that we can change in the computational procedure is expansion coefficients, how the atomic orbitals enter into molecular orbital. And mathematically, Hartree-Fock theory is a procedure to find expansion coefficients. So after doing partial convolution of the Hamiltonian over all but one electrons, we are getting this one electron Fock operator. And when we were last thing before we departed from the meeting last time was to compute expectation value of electron-electron interaction. So we were putting Coulomb orbital between Slater determinants for ground state multi-electron wave function. And then in between there is this Coulombic attraction. And then when we were opening the brackets, we got one term including positive sign, which is Coulomb repulsion, and another term which was including negative sign, and we called it, I don't know if I introduced the word, but it is called exchange. So due to antisymmetry of the wave function, one is getting additional term into energy which stabilizes molecule, makes our computational prediction more realistic. We predict that most of the molecules will be stable. Okay. So done with previous meetings, and now starting the new meeting. So there will be a couple of figures related to scientific achievements of Richard Feynman. So here is Wikipedia page about him, and you is aware of this scientist because he did work in Los Alamos, and some streets are named after his name, and even there are some postdoctoral fellowships under Richard Feynman name. But in relation to our course, I want to bring up an interesting feature that Richard Feynman brought to modern science. So when people consider interaction of several quantized particles, equations get very, very long. And those equations that we already went through are very simple. If one gets into further away without computers, the equations are taken much more than one page. And one of the achievements of the Richard Feynman that he introduced a way how to represent equations with figures. So it's not only funny figures to entertain audience, it is figures that are equivalent to equations, and one can do mathematical manipulations and analysis of equations in the graphical form. So here is an example of the figures, also from Wikipedia. So there are straight lines with arrows, wavy and wavy lines. So straight lines correspond to particles and wavy lines to interactions, which simplest particle is electron or positron, and simplest interaction is exchange of photons. But there are much more particles that we do not touch here, but Feynman diagrams are applicable there. So after this introduction, let me go forward to subject of our course. So on the top side of the slide, there are two equations with which we did end our meeting last time. So in the top left, there is an equation where index of electron and number of electrons do coincide, 1 and 1, 2 and 2, before interaction, and here again 1 and 1 and 2 and 2. So such combination gets plus sign, we call it term number 1, and it does correspond to repulsion. Positive energy. Below is the graphical representation of this equation according to Richard Feynman. So we do have the I'm going to highlight. We do have first electron in wave function 1, which interacts with second electron at point R1. And after interaction, it continues to exist as an electron, but we are considering the conjugated thing, but it's still electron number 1 in the orbital number 1. Here. At the same time, there is a second electron, number 2, in orbital number 2, and it interacts with first electron at point number 2, and then departs from interaction. So this diagram and this equation mutually replace each other, and it corresponds to energy of interaction between two electrons. Now, let's focus on the second part, on the right part of this figure. So we did call it term number 2, and there is a minus sign, which is critically important. So minus sign means it is stabilizing term in the interaction, which means molecules will be stable. And by the way, the interaction is symbolized by the wavy line. Okay. Now let's look on the second equation. So we start from electron number 1 in wave function 1, and after interaction, suddenly electron number 1 occurs to be in the orbital number 2. But we do not have a mechanism for jumping electrons between orbitals. So at the same time, the electron number 2 was starting in the second orbital, and after interaction, it continues in the orbital number 1. So this term corresponds to electrons just swapped from simultaneously swapped and exchanged their places. And mathematically, it comes from Slater determinant, from antisymmetry principle. Physically, it corresponds that molecules will be stable because of negative energy. And on the Feynman diagram, we show that these lines for electrons cross each other. Okay. If we forget about antisymmetry, then multi-electronic wave function is just Hartree product of one electron orbitals. But okay, but we do know we do need the antisymmetry. So what if we perform the part of the Coulombic interaction, if we consider, if we remember our attempt to do the partial convolution of the Hamiltonian in respect to one electron and keep it as an operator in respect to another one. So if we do convolution in respect to second electron and keep it as operator in respect to the first electron, then we have everything related to the second electron. We do integration, and by applying this operator to the first wave function, it's same as regular quantum mechanics with one electronic operator. If we make convolution with wave function of the first electron, then we will get Coulombic energy. So once again, this operator with partial convolution is able to act on the electron wave function depending on first electron. How can we represent this convolution on Feynman diagram? So we need to keep things related for the first electron and remove everything related to the second electron, or keep it as a black box. So here it is. We just cross out by a box everything related to a second electron and tell that it is our Coulomb interaction with mean field created by all other electrons. So this is a result of our partial convolution. If you do the same thing, no, wait. If we try to apply this procedure to simplest possible model in the world, to one-dimensional particle in the box, then this Coulomb operator will look as this colorful matrix. The ground state in the box is one peak, and upon convolution, the action of this Coulomb operator slightly repel electron density from center to the sides, but it stays wave function stays positive. Now, if we do the same partial convolution over second electron over the exchange term. Then we are getting this term that will act again on the electron number 1 in orbital 1, but by implementing the prescription of our second term due to antisymmetry, it is equivalent to replacing the argument and actual wave function from the kernel of this integration with each other, and then this box, which will correspond to exchange, will correspond to a diagram where electron comes to point in space 1 and suddenly comes back, bounces back in the different orbital. And it is counterintuitive. It is not healthy for human brain to think about it, but including such diagram, including such bouncing back with changing of the orbital, is critically important to make correct predictions of molecules, of predicting that molecules will be stable. And if one implements the same idea for simplest model of harmonic oscillator, acting by exchange operator of the ground state, and it is a 2 electrons in one-dimensional potential. Then upon acting of the exchange operator, there appears 2 peaks, and the sign of wave function becomes negative, which later on will correspond to negative energy. So this slide is absolutely senseless for all of us because we are not planning to do theory derivations in this course. But if hypothetically we consider moving forward into derivations, one may want to accept general notations for both regular Coulomb and exchange. So if there are orbitals with indices R, S, T, U, and molecular quantum chemistry doesn't have anything except orbitals. So one can put this RSTU as a list of orbitals involved into interaction, and depending on whether these orbitals follow each other or exchange their order, it will be either Coulomb or exchange. So if 2 first indices coincide and last 2 indices coincide, it will be Coulomb. First and last coincide, and then second and third coincide, then it will be exchange. Okay, I think we are done with the lecture. Thank you much for tolerance and patience to these materials. And now I would like to invite everyone to go to the practical part. So for this, please log into Photon and maybe keep another window on your local computer if we need to migrate files. So I am going to bring, and if anyone has questions on this lecture material, please feel free to ask verbally right now, type in the chat room, or send an email. I will be extremely happy to address any questions. I got the disconnection because of the lack of activity. I need to re-log in. I will take help from my classmates later. Uh, Jayanta, I'm very flexible, but please consider of doing things and submitting. Don't wait for me for practical part. Currently, my phone does not support any microphone. Oh, but you can, yeah, I will not wait, but you can connect from your computer. And also you can go into QBB 132. I think the camera and microphone are activated. You can just sit in this room and use it as an interaction tool. Okay, so I'm going to network problem here. Oh, okay, yeah. Thank you, Jayanta. So I did log into the photon and navigating to the directory where we do exercises for this class. Summer. So I'm going to my directory. Wait. Wait. Okay. So then I am starting the Gauss U, and I did create the structure before. So you may try to, if you want to rebuild it, but I suggest everyone takes it as an example. So let me share the structure so that you save your time. So I will copy. Um, So if you need, you can either build it or take this example. So I did place it in the. Let me show the path. So right now our goal is not to build the model, but to change spin and multiplicity. So I did shared the location of this input file to all of you. So probably for saving time, you may want to just copy it, go to your directory, open subdirectory for today's lab, and take this template. So if I am modifying, if I'm looking onto this file in the Gauss view, and I have no doubt that each of you can build this model. It's not as challenging. So it's 19 atoms, a little bit more than in our previous model, but still quite small. And ideal distance, the distances are not primary goal. Primary goal is to focus on the multiplicity. When we will be doing projects, then one would need to be very careful with structures. So when you are setting up calculations, when making Gaussian calculation setup, so we are using only energy, no optimization. We keep line of TDZ basis set, Hartree-Fock method, and it is important. Gauss view often prompts good keywords, but here one needs to select unrestricted. Unrestricted means that number of electrons with spin up and spin down could be different. Then charge, typically we used 0. Here we need to do 3. If please type or say if you want me to explain a little bit more why hexa aqua titanium should be in 3+ configuration. Okay, I do not see any questions, which seems that you are fine with this settings. So if one would try to run this model with different charges, then charge different than 3 will substantially increase energy. So the minimum for this model is at charge 3. And then there is another selection for spin multiplicity. Let me show. Here there are numbers, there are words, doublet, quartet, sextet. When we were doing previous model, these options were not available. Janice, can you explain what is going on? Why singlet and triplet did disappear from this list?
You have a charge of 3, so you can't have a singlet because it must have an unpaired electron of some sort. And since you can't have a triplet either with a single charge free, you can only have doublet, quartet, sextet. You can only have even number spin multiplicities.
Okay. And if I do know how many unpaired spins are in the model, how to get this spin multiplicity? Like if
based off continue, sorry.
No, if I know that there is one unpaired spin, how do I know what will be the multiplicity? If S equals like 1/2, spin equals 1/2, what will be the multiplicity?
If spin equals 1/2, then the multiplicity would be 2. So
and
that would be doublet.
Which formula did you use?
2n plus 1.
Okay, yes.
Where
yes.
n is the spin number.
Many thanks. Perfect. Anyone wants to doubt this explanation, or anyone needs more details? Let me type it in the chat room. So multiplicity equals 2 times S plus 1. So where S is total spin of electrons in the Planck in the units of Planck constant. So for spin equals 0, one is getting m equals 1. For S equals 1/2, one is getting m equals 2. For S equals 1/2 plus 1/2, m equals 3. So, Kristen, can you please tell or type what does this multiplicity 1, 2, 3 mean? How to interpret it? Any suggestions? And everyone is welcome to provide the suggestion. Yes, it is 2s plus 1 rule, correct. But what, thank you, Jayanta, but what is the interpretation? What does it mean, the like doublet? What is two what? Two of which objects? Well, I think first of NMR and multiplicity relates to the number of protons that are chemically equivalent. Not wrong. Okay. States. Yes, states. So it is. Thank you. The degeneracy. Like if we do not have magnetic. Yes. Yes. If we have magnetic field, the energy of doublet of well, doublet has two states that have the same energy but different spin, right? So it is degeneracy of the state. And if it is triplet, there are 3 states with the same energy. So multiplicity means degeneracy number in absence of magnetic field. Please object if you do not like this explanation, or if everyone is fine, let's go. Yes, degenerate states. Yeah, thank you, Jayanta. So here we select doublet, but if we would change charge to a different number, then Gauss view will prompt different set of spins. And after that, one can go into submit. And I already did it, so it's a little silly for me to rerun it. I can maybe, no, I shouldn't, because it's already save version B. But it will be a quick calculation that submit the following to the file to the Gaussian. So this is again a very small model. We do not need cluster. So please do this calculation, and so you see it took few seconds. So I am, and you see that there are new files .log and .chk. So I'm going to browse through directories and see if you did arrive to this files, so that we can continue together. So I will inspect the files. I hope I didn't get disconnected. Mahima, do you need help? I do not see. Let me go to your directory. Oh, yes. Are you logged in?
I think I'm trying to do.
Okay. So so please do not hesitate to tell if something doesn't work. I am here intentionally to help. So we make copy of the file into here. Mahima, do you remember the password? Can you log in? Do you need the exact command for logging in?
I think I am in that photon.
You are on the photon.
Already logged in.
Okay.
Yeah.
Are you in your directory?
Yeah.
Okay. So can you open? I already transferred the input file into your directory. Can you open it with Gauss View and watch and inspect it?
Yeah, the ghost view is open.
Okay. Please open this file, titanium 06H12 charge 3 multiplicity 2.
Yeah.
And then please try to submit it to the Gaussian. It should be it should be rather simple. Okay, I will look into your directory once again, and when I look there again, there should be the file that ends with .log. Let me know if there will be difficulties, but it should go quite simple.
Okay.
Do you see? Were you able to see this molecule on your screen in Gauss view?
Yeah.
Okay. Can you do the calculate Gaussian calculation setup?
Gaussian calculation scheme.
Uh, yes. Calculate Gaussian calculation setup. Do you see what I'm showing? It's like in the menu of the gray area, you go to
Yeah.
Gaussian calculation setup.
Yeah. So I need to build this molecule.
No, you skip. I already built it. You need just launch Gaussian. So just click submit. That's it.
Oh, I was trying to make that one.
No. The life should be easy.
Oh, okay, then I pasted that scratch 001, that one, and I opened, and now
Wait, wait. Which are you in which directory are you? If you type pw,
The one that you said.
if you type pwd,
Yeah, the one that, what?
pwd. If you type pwd, what do you see?
Yeah.
You can share your screen, and I will quickly navigate if something is problematic, but it should be. Yeah, Joanta, it's not a problem. Mahima, would you like to share your screen?
Yeah.
Okay. And everyone is welcome to follow the steps from the slides. So maybe you'll be able to complete it much quicker than I'm showing.
Is it showing?
No, there are some technical. No, maybe the connection is not as quick, but okay. So it did stop sharing, but oh, I think it works. Yeah. Oh, good. Ah, okay. Okay. Can you? So after right now, do not change things. Let me just quickly tell Gauss view dot exe, and then one needs to do this shift ampersand, shift 7. Otherwise, it doesn't recognize the commands.
Oh.
Can you show your Gauss view window, how it looks like? Right now you're sharing the panel with MobiX term. Can you share the panel with Gauss view or the whole display? Whatever is.
Oh, I just did the panel only, I guess.
Yeah, but it's better to show the whole display because we need to jump between panels. Okay, so let's go file open. In this gray, just file open. Click Mahima. Click your directory. Click on your directory. Yes, and select this titanium 06 H12. Open. Okay. Now go back to this gray thing. Yes, and click calculate. And the first one, Gaussian calculation setup. The first one.
Okay.
Now click method. And you see that everything is already set up. So ground state, Hartree Fock, Lionel 2DZ, charge 3, spin doublet. Now at the bottom there is a button. At the bottom there is a button, submit. Please click it. I do not see. Lower.
Yeah.
You
Submit.
see? Yeah, submit. Submit. Yes. Okay. And now just click OK. So you see the job is already done.
Oh, okay.
Okay. So you see it's not very complicated. Now you can do a little experiments if you want to click different buttons, but I need to go over everyone in the class and check that things are going well. But you are in a good standing. Okay. I'm starting to share my screen now. Okay. And so if I look in the directory by Mahima, ls-ot, before it was only .com, now you see there are two new files, .chk and .log. Let me go back to the common directory and see. So Jayanta told that he has left. Tao is not connecting today. Let's go to look to what. Lishu, do you have directory for yourself? If are you logged in? Lishu, are you logged into the server? Do you have a directory? Please let me know what is going on. I do not see directory for yourself here. I see. I will go to your directory very soon. I just check in with Lishu Shah. No. There is a collaboration with University of North Dakota, and there is a visitor from Professor Tao Yu group, Li Shusha. Lishu, let me know if are you using different server, or you need help in opening directory or logging in. Please type or answer or send an email if you do not feel comfortable speaking out loud. Okay, I do not hear answer, so let's. But feel free to talk to me. Without doing this practical exercise, it doesn't make sense to attend these meetings. It's practical exercise is most important. Okay, let me go into the directory view, cd web 13. Okay, very good. So if you can, please try to follow instructions from that are from slides or from Word file. After I will check that everyone is fine, I will start doing things myself. Okay. Mahima, you, Kristen. Oh, Kristen, you are ahead of everyone, including me. You should teach us what to do. I'm very happy to see your progress. Okay. Kristen. Let's go to Janice. .log.chk. Okay, very good. Who else is today? Still doesn't have an account. Lishu, you can go into directory of Professor Tao and be his representative. So just open like lab 13 there and do exercise there if you do not want to open your. So Lishu, you, Jing, Maxima, Kristen, James. Okay, I think everyone is. So I'm going back to my directory. And I'm going to make a little shortcut, which is not exactly what I originally wanted to do, but Mahima may appreciate it, and you all will appreciate it. So let me, and Janice also, before doing hard work of analyzing data in command line, let's do a little bit of easy mouse click analysis and interpretation. So I am going open Gaussian checkpoint file, selecting the file that we just created, open. So I'm opening the check file, not .log, but check file, and then calculate, not calculate, results, and going to surface contours. So after I am going to surface and contours, it shows three panels: cubes, surfaces, and contours. So I can click new cube, and this mouse clicking procedure in some sense replaces the command line things that we will be doing in a few minutes. So types: molecular orbital, total density, alpha density, beta density, spin density, ESP. So if you have a reliable connection to graphical environment to Gauss view and you hate command line, you may try to do it, but later on you will be doing command line. Now let's see what is written there. So it tells there are 35 occupied alpha and there are 34 occupied beta. Let me ask Janice how to interpret this little recording: 35 occupied alpha and 34 occupied beta.
So I would say that means spin up and spin down, where alpha is, I believe, spin up, and beta is, I believe, spin down.
Mm-hmm. And why these numbers, occupied alpha and occupied beta, are not equal?
Well, because we have a multiplicity of 2, and so we have a free electron, and that's going to cause an uneven orbital splitting.
Okay, very good, very good. Yeah, thank you. So I'm selecting Homo alpha, selecting maybe medium, and clicking OK. So the procedure that I'm doing by mouse right now, mouse clicking, is replacing form check and cube gen. Clicking. Okay, maybe it takes too long and it works in the queue, but um, this procedure in maybe do oh, okay, so it appears cubes available, so it gets with a little delay, and after this cube is available, I can plot it by clicking new surface. And here is the HOMO for alpha electron, and it has majority of on the d orbital of titanium, but it is also hybridized with something on hydrogens. And then I can do HOMO beta and compare if they look similar or different. So this is a backup to those of us who hate command line operations. So Janice, as you did sign up for plotting, for explaining how to plot orbitals in your presentations, you may want to explore this opportunity more and include it into your presentation and teach others. Especially, you will get a lot of likes to your presentation if you explain with more details what is ESP. This this subject ESP is favorite tool of organic chemists. So and it is like minimal activity that synthetic organic chemists prefer while running Gaussian. We will be doing a little bit different things, but if you explain it in your presentation, it will attract a lot of good attention. Okay. Okay, thank you. So I am going back to the command line and opening this little cheat sheet for myself. So before going to this cheat sheet, I'm going to scroll through the log file. So if I'm scrolling through this log file, here there is a little, I would present it as a surprise, but now after discussion with Janice, it's not a surprise anymore. So before we used to have only alpha OC and alpha VIRT, right? So before today's meeting, we did have a list of occupied and unoccupied orbitals. So occupied goes up to here. This is HOMO, and then starting there, it is unoccupied. But in this spin unrestricted Hartree-Fock, in this calculation with even number of spins, you see after alpha eigenvalues, there are beta eigenvalues. And what I would like to attract your attention to, if I'm focusing on occupied, the last occupied for alpha, if I count 5 times 7, it will be 35. If I look for beta energies, it will be 1 less, right? And the energies, they're not drastically different, but they're different. So the last occupied for alpha is minus 1.04, and highest occupied for beta is minus 1.07. Now, if you look for a segment for virtual, for alpha, the lowest unoccupied is minus 0.44, and for beta it is minus 0.42. So we do see that they are not identical. And this is very typical. Sorry, right now this. Okay, I just brought back screen. So few things were not recorded on with this voice. So this difference in alpha and beta orbitals energies is a standard feature for transition metal complexes, always, and it is also often observed for reactive transients, radicals, and explosives. So this high multiplicity happens when system is either transition metal or something unstable. So a lot of useful calculation can be done without this multiplicity, but in order to be fully equipped computational chemists, we need to go over it. So there are two lists, and in order to generate density of states, we need to extract these two lists and build density of states out of them. So I am copy pasting thing from the cheat sheet. I'm typing Perl and then name of the script. Let me type it in the common chat just in case. And this is not the whole story. After this Perl and name of the script, I need to type the name of the .log file, and then let me look on this cheat sheet. The same four parameters as we did last time for single density of states. So 1000 is a good number. Then I will use 0, 1 to have broader lines, and then 5. Well, instead of 5 and 5, I will type 3 and 3. And then it works without error. And if I type ls-lt, there appears new files. If I look through them more, EOC, it parses things related to alpha. And for virtual beta. Now I want to run the same script with but replacing the word alpha into word beta in the script name. Let me copy paste it into the common chat, and I hit enter. Now I do ls-lt, and I do see that there are two files, DOS beta and DOS alpha. So I'm looking through the cheat sheet and copying this DOS alpha and DOS beta into DOS alpha.log and DOS beta.log. So cp DOS alpha into DOS underscore alpha.log, and the same for beta. Okay, after this, let me see. I do have two files with short names, DOS alpha, DOS beta. So now I want to combine the data from these files into edit undo. Instead of copying, I edit copy. Okay. So I'm typing this GNU prod, GNU prog. If you do not like this command line things, one can download these files DOS beta and DOS alpha and plot them with your favorite graphical program like Origin or Microsoft Excel. So this script does nothing but plots content of the files with first column being X and second column being Y. So if we do head DOS alpha.log, first column is energy and second column is height of the peaks. ls minus lt. So we do have file DOS spin go9.ps. I want to convert it ps to pdf from PostScript, which is ancient, into PDF, which is modern. Enter. And in order to look through this file, CP. So one can transfer files either in a command line everything which ends with PDF space period into here and then typing password. So but if you are using MOBA extern, one can transfer files by using left panel and do it in a mouse operated fashion. So I did transfer file, and let me check how it looks like. I'm putting TOP to prevent log out. Going to the Acrobat. And you see my activities with a little delay because of the transmission. Okay, so this figure shows that both for alpha, which are placed in the top, and beta spins, there is a noticeable gap of like 15 electron volts, which is wrong. The Hartree-Fock method is historically important, but for absolute values of observables, it typically predicts much bigger band gaps. So we use it only for educational purposes. Actual band gap for this material is expected to be like 2.8 electron volts, so about 4 or 5 times smaller. But what is good here that it predicts that occupied and unoccupied orbitals are have negative values, which means this molecule is very stable, and the gap is open for both alpha and beta electrons. But the gap for alpha is a little smaller, so if the system is emissive, then it will emit from alpha transition. Let me, and since I increased the parameter for the width, it shows, notice bigger width for each individual peak. The mechanism for this width is thermal line broadening. So let me scroll through directories and check if this PDF file is available in the directory of everyone in the class. Mahima, are you a little discouraged with too many commands in the command line?
Yeah.
Okay, but it's not a problem. So please try to copy paste things from the common chat and paste them in your directory and see what happens.
Yeah, I.
Please try, and you can share a screen, and I will watch how you do it. What we are doing is not terribly complicated. Let's do it together.
Yeah.
Would you share the screen?
Yeah.
Okay. Please try to share it once again. I think it stopped sharing. And yeah, we need this. So let me give a comment. You need either open second panel and connect to photon, or type Control C here, because what is let me explain before we do. Right now you didn't put this Shift 7 after Gauss view, and Gauss view blocks all command that you are typing. So let's kill Gauss view for a moment. If you type Control C, it will kill Gauss view but enable typing commands. Good. Now please type ls minus lt.
ls minus t.
And there is a space between minus. Minus. And no space before t. But hit enter. You didn't make anything wrong. LT. ls minus lt. Let me type in the chat line. ls minus lt. Try once again. ls space minus lt. And do not put space between minus and lt. So ls space minus lt.
Yeah.
Good. Now cd space Mahima.
Oh,
CD space Mahima. Okay. Now do arrow up twice. Just hit arrow up to repeat this ls minus ot. If you hit arrow up, it will repeat your previous command.
what was it again?
If you hit the symbol of arrow up, it will bring back your previous command. If you hit it twice, it will 2 commands ago, which can be useful.
Oh, like this? Oh.
Hit enter. Try once again. Find the one that you was a ls space minus lt, or you can correct it quickly. Good.
Oh, yeah.
So you see the latest file you have created is titanium06.chk, and second one .log. Now let's copy paste the Perl line from yes, from here. Okay. Now, yeah, space. Do not hit enter. Do not hit enter. Space.
Oh, I did.
Not a problem. Not a problem. Do Control C if it gives you hard time. Control C to stop it. Okay. Now arrow up to bring it back. Now space. PL and then not backspace but regular space. The biggest key on the keyboard.
Oh, so the same command. I will do one more.
Okay.
Oh no, it's not coming.
No. Do not do it. Do not do it.
I think I will go back then.
Okay, just do paste the thing once again.
This one?
Yes. Space. Okay. Now hit not backspace but regular space. Yes. Space. Yes. Now copy paste the name of the .log file. It's no. In your command line. In your command. No. Okay. Just go to your command line, please. And now.
Okay.
The best thing is just copy paste, or you can type it titanium 06 H12. Hit tab and it will continue automatically. If you, tabulation on the left part of the keyboard, there is a tab key, and it tabular. And it will automatically continue stuff that you are typing.
So should I press the shift button?
No. Just tab. Tabular.
Tab. Oh yeah.
And now type LOG. Space. And now I'm going to give you 4 numbers. 1000. Space. 0.1. Space. 3. Space. 3. And hit enter.
Space
Now hit enter.
Okay.
Return. Very good. Now please hit tab, the arrow up. Arrow up to repeat, yes. And now hit arrow left to the middle of this line and replace uppercase alpha with uppercase beta.
This one?
So replace alpha with beta.
Just replace alpha to beta.
Yes. Uppercase. Enter. Very good. Now do ls space minus lt to check which files do you have. So you do have DOS underscore beta and DOS underscore alpha. So 3 more commands. So please type cp for copy, cp, not cd, cp. Yes, Charles Peter. Yes, space. DOS underscore alpha.
Underscore alpha?
No, DOS, DOS underscore alpha. One of the files that you see in this list, DOS underscore alpha.
DOS cos?
Alpha. No, alpha. Alpha. And hit tab that it automatically continues.
Enter?
No, tabular. That it,
tab. Yeah.
Okay, and now type by your hands once again DOS underscore alpha. Underscore alpha dot log. Log should be lowercase, yes. Enter. Hit enter. And now arrow up to bring this command once again. And replace, now please use arrow left and replace alpha to beta in 2 times in first and second file name.
So should I change the alpha to beta?
Correct, yes. Uppercase. And also at the beginning of the line, yes. Make sure that there is no you have double underscore. It should be only one. Yes, hit enter. And now please copy paste the command from the chat room that starts with GNU plot.
This one?
No, a little the one before it. Yes, GNU plot.
This one?
No, next. GNU plot space tilde, yes.
Yes.
Copy and paste here. Enter. And now type ls minus lt. ls space minus lt. Not an, yes, minus lt. Enter. So the latest file, you see dos underscore spin underscore go9.ps, right? So the latest file that you created. Now, PS is ancient format for graphical files. Let's convert it into PDF. Let me type it in the chat room. PS to PDF WR space. So type, copy paste this command.
Enter.
No, space. No, arrow up to repeat this command. Arrow up.
Space.
And now type name of your PS file. DOS underscore spin. You can hit tab to continue. Or you can type it completely by hand. Yes, hit and now hit enter. And now do ls space minus lt once again. Enter. So now the latest file is dos underscore spin underscore go9 dos pdf. Now we need to download this file to your desktop. Let's do it together. So let's do manipulation by mouse with your left panel. So you see there is a left panel with file names.
Yeah.
So let's scroll up until scroll up completely to the top. And you see green folder with arrow, green folder.
Oh yeah.
So click there. Double click on the folder. Click. Now let's scroll up once again. Let's scroll to the top up again and double click on the green folder. Now scroll once again and see Scratch 001. Yes, double click on the folder. Find CHEM676. Double click on the folder. Now find the summer. Double click on the folder. Find Mahima. Double click on the folder. And let's scroll and see. Let's scroll through and find. Yeah, you see this PDF file, PDF symbol.
Oh yeah.
So you can either double click or just pull, drag and drop it on your desktop. Also, there is a, if you navigate to the top of this panel, you see, oh, okay, Acrobat Reader, yes, please open. Very good.
Oh yeah.
You see, it works?
Oh yeah.
So you did everything yourself, right?
Yes.
So I'm very happy for you. Congratulations. It's a really important skill that you can use for nickel catalyst or other metal organic complexes that you are doing in your research. Okay.
Yeah.
I'm going to share screen myself and check if everyone is on the same page.
Thank you.
Oh, my pleasure, my pleasure. I'm happy for your success. Okay. CD space. T. U. CD of 13. S minus LT. Aha, I see, I see. You're progressing really, really well. Okay. Maxima U CD. Potential cube. Okay. Okay. DOS spin. And let me check if Lishu is practice this. Maybe in the directory of Professor Tao. No. Lishu, please plan on practicing these things. And if you're doing it on the different computer, then you need the scripts which are needs to be transferred, and it is not easy. Um, maybe 13. Okay, so the next step. Let me open my cheat sheet. So next thing is to do form check of the check file. And let me copy paste, but this the name of the file can be slightly different. Form check is the same for everyone, but name of the file can be different. And then one is typing the command to generate the orbital. It doesn't. Huh. doesn't like. Oh, of course, it's not. It should be not check, but form check. Correct. FCHK. Okay, so after this, before we were doing mo equals number of orbital, and then we were naming the files mo.cube. Here we do alpha and beta, and just to save time, we do AMO and BMO for alpha and beta orbitals. And after this files have been generated by CubeGen, so basically it should give the same thing as we already did before we went to density of states. But the cube files, after they have been created in the command line, can be visualized either in Gauss view or in Avogadro or JMO. So in Gauss view, I'm doing open. I'm selecting the cube file and selecting AMO. So 36, which should be Lumo. Click open. And after I have downloaded the cube file, I can go into results, surface contours, and it already shows the cube. And for available cube, I can go to surface action, new surface, and it shows alpha molecular orbital 36. So sometimes it is more healthier to plot, download, pack them all into Word or PowerPoint, and only then to go to analysis, because like rotating these orbitals may take longer time, since it is a large amount of graphical information. So if I do have things that if Gauss view works properly, I just do a screenshot. If it doesn't work, I can do file, save image file, and call it AMO36 TIFF or any other form. And then so the snapshot, you see the symbol of rotating marker, which means it. Oh yeah, Kristen, thank you for staying here. See you on Wednesday. I think we are done with our program. I complete this little exercise, and we will disconnect very soon. So this capturing image does work even if the screen doesn't show anything. So it's graphical processing of information. And you may download the cube file on the local computer and open it with either, let me type in, we already used JMO, we used Avogadro, and there is also very much recommended software which is called VMD. So VMD will be used in the rest of the course, even when we finish with Gaussian and go with another software, WASP. VMD is an excellent visualization tool. And the fourth one is Vesta. So there are more pieces of software, but each of them is able to open cube files from Gaussian and display them. So there is no critical need for the Gauss view. It's just one of the tools. So capturing image, coming to completion, 72. So we're close to completion. Done. So I can go into my local directory and download the TI. Let's download everything that starts with AMO into local. Just use. So I'm downloading both cube and TIFF file. And for the TIFF file, let me go to the team. So here's our workshop. Let me add a slide at the bottom. Insert new slide, and I will insert picture from file. So I hope very much that this. So first I will insert the desktop that just screenshot, and so new slide. And now I will insert the TIFF file that has been created without looking on the graphical file. So MO36 TIFF. Okay, so the image is not worthier than it was, and if I open this Vesta software, I should be able to plot this alpha molecular orbital as well. Let's check file, open. AMO36. Okay. So it does show this orbital which has maximum on titanium and something on like hybridization between hydrogen and oxygen. Okay, in the cheat sheet, I do have few more things. So if one types CubeGen density, CubeGen spin, and CubeGen potential, it is things that provide additional options to analyze electronic structure. But I think it is enough for today. Let me check for the questions. Oh yeah, Janice, I think we are done. So if anyone has questions, I'm happy to answer. So I will wait a little bit for the questions, but meeting is done. Everyone is welcome to disconnect. So, yeah, thank you, Mahim. I'm very happy for your success. Thank you. Let me know if there are more questions. My pleasure. My pleasure. I hope the recordings went well, and I plan to share it. Literally, let me know if you want to ask any questions verbally. Okay.